Let me get started with this. Good morning. Oh my God, so good to be back to Europe. It's so good. It's actually not my first time this year in Europe. It's the third time, but it's the first time in Belgium since you know what happened. And I'm very excited to be here. I mean, it's amazing. DevOps is happening again. Who is here for the first time at DevOps ever? Wow, more than half are here for the first time. For those who are here for the first time, who's from Belgium? Okay. And who's not from Europe? Okay, a couple of folks from London. All right. My name is Bruno. I will try to make as many jokes as possible. If it's good, please laugh. If it's not, you know what to do. I also laugh. I can get started. I'm from Brazil, but I live in Canada. I actually arrived here yesterday on shorts and a t-shirt, and I was like, still summer. I got used to the weather over there. And Belgium is like my second best favorite place in the world. Of course, beer, but also people and technology and friends that I've made here over the years. And also DevOps. So, it's an honor for me to be here on the first slot on Monday morning with you all being here with me. So, thank you. Appreciate it. All right, so this talk is about secrets of performance tuning Java on Kubernetes. So I will ask a lot of questions. We have 3 hours. We're going to have a 30-minute break. So we're going to go. Actually, I should hit start on my phone because I want to keep track of time. We have a break in 1 hour and 15 minutes. And then we're going to go for 30 minutes to detox all the YAML that we'll see or get ready for all the YAML you might see. We're going to learn about Jvm Ergonomics, Jvm inside containers, Kubernetes, resources, constraints, planning, all of that. And unfortunately, or fortunately, I don't know, a lot of YAML. So bear with me. Before I dive into that, I would appreciate a little bit of your attention because we from the Microsoft Java Engineering Group, we really want to share some information with you all to understand why we have a Java engineering group at Microsoft and why we are so invested in the Java ecosystem. So, of course, Microsoft has a cloud, Microsoft has tools, but what is it? What is this thing, Microsoft for Java developers? And we like to talk about two things here. How and why we participate in the Java ecosystem, and how we are using Java internally inside Microsoft. So this will take only 5 minutes, and I would love to take questions if you want, or you can save questions for later, it's fine. But I would really want to share this information with you because I believe it's important we make those connections and establish or reestablish that relationship between Microsoft and the Java community. So we have been, of course, participating in the Eclipse Foundation through two major working groups that you may be familiar with. One is the Eclipse Adoption Project, and the other one recently announced the Jakarta EE and Microprofile working groups that Microsoft is now a member. We also collaborate a lot with VMware on the development of Spring, especially integrations with Cloud and Visual Studio Code. Last year, we became a member of the Java community process. And there is a voting coming soon for the executive committee. Microsoft may or may not be on the ballot for that. GitHub and Visual Studio Code, of course, you all know about. So we had this JCP announcement last year, but it's really not about how we do things on the paper, it's how we do things on the code. And one of the reasons Microsoft wants to participate in the Java ecosystem is because we believe all developers deserve awesome tools, Java developers included. Visual Studio Code became the third most used editor. I won't say IDE because it takes 15 extensions to become an IDE. But once we install 15 extensions, maybe 25 more, it's an IDE. But it's a great editor, and 1.7 million Java developers actively using it. But there's more. GitHub Copilot got announced recently, and I'm going to show throughout my demos how GitHub Copilot can help Java developers. GitHub Actions, of course, for CI/CD. Playwright, I won't be showing Playwright, but it's a tool that allows you to do web applications end-to-end testing in the browser. And Windows subsystem for Linux. Because if you're on Windows, you really want Linux. And if you cannot have Linux, but you have to use Windows, at least you got Windows subsystem for Linux. We have our Microsoft build of OpenJDK. We ship 11 and 17, and we will be shipping future LTS releases. And those LTS releases will be made available for Microsoft tools and services. We participate in the Eclipse adoption, as I mentioned before. We recently added backport for Alpine Linux on the Adoptium build for Temurin JDK 8. That work was done by Azul Systems and Bellsoft, and our team took those changes and incorporated into Eclipse Adoptium. So now you have Alpine Linux support for Eclipse Adoptium for JDK 8. I'm not saying you should continue using JDK 8, but if you have to, now you have Alpine. And these other resources for developers, a developer portal, developer.microsoft.com/Java, and docs.microsoft.com/Java. But what is really interesting is how we use Java inside Microsoft. Today, we run roughly 2 million JVMs in production inside the company, not counting all the Azure third-party customers. These are just JVMs that are executed by Microsoft for Microsoft. And it does include LinkedIn, it does include Yammer, it does include Bing, and it includes also other subsidiaries that Microsoft acquired in the past 8 years, Metaswitch and Nuance or other companies that became part of the Microsoft family. And one thing that I like to say, like, okay, who uses Bing? Who uses Windows? You all use Bing and you don't even know. When you hit the start menu on Windows and you get web search results, those are coming from Bing, not Google, not Alta Vista, not Yahoo. Those are coming from Bing. So you all know, you all use Bing. So next time somebody asks, next time I come back and I ask, are you using Bing? Raise your hand if you're using Windows. I don't use Bing. You can see that it's a Mac. I don't use Bing. All right, jokes aside, the other thing that I like to say is Minecraft. Everybody here knows Minecraft. Everybody, I hope, knows Minecraft. Mojang Studio got acquired by Microsoft years ago in the most expensive Java software ever sold in the world. For $7 billion, Microsoft acquired Minecraft Java Edition, and it still lives under Microsoft. And it's running Java 17. Who has a kid playing Minecraft? Okay. Of those, keep your hand up. Keep your hand up. Okay. Of those that have a kid playing Java 17 Minecraft, which ones of you are still running Java 8 in production? Okay, talk to your kid. They can help you. So let's move to Java 17, right? That's the message. If even our kids are playing Minecraft in Java 17, I'm sure we are able to move to Java 17 in production on the server. And yeah, we do use Java a lot. Microsoft runs on Java. And I got some facts to share with you. The Azure infrastructure behind the scenes when you go to the Azure portal and you say like create a VM or create a Kubernetes cluster or create a container registry to host my image, all of those messages, they navigate through an Apache Kafka cluster with 500 billion messages, 200 terabytes of data per day. And Kafka, as you know, runs on top of the JVM. LinkedIn has more than half of its staff Java developers. And they have roughly 2,000 microservices implemented on the back end with 5 trillion messages and 5 petabytes per day on their Kafka clusters. And they have other Java technologies in use as well. Some that became Apache projects, and some that are still projects inside LinkedIn. Some of them are open source, some of them are still closed source. But you can check on the LinkedIn engineering website for links to their GitHub projects. Minecraft, Yammer, and Bing also massive amounts of JVMs and data behind the scenes. So the Java ecosystem is extremely important for Microsoft. It's extremely important for all of its businesses. And we use and collaborate on a variety of open source projects. There is one that I found out last week, Apache Cassandra is heavily used as well. And when the team that manages Cassandra inside Microsoft saw this slide on another presentation, they were like, wait, you didn't include us. And they sent me the details. I still did not update this, but it's also massive. They have huge Cassandra clusters running on top of the JVM. And you can learn more about this information from this PDF on aka.ms/MSFT for Microsoft applies Java. And you have more details about how we are using Java and collaborating in the ecosystem. All right, that took maybe a little bit more than 5 minutes, but still under 10. Let's talk about the agenda for the next, the main part. So part 1, before the break, I'm going to walk you through Jvm Ergonomics and garbage collectors. And second part, we're going to edit a lot of YAML files. We're going to break things. I'm going to delete pods, redeploy pods, deployments, et cetera, and run performance benchmarking live so we can see how these changes will impact the performance of your application. And what is the conclusion of this whole exercise? What this is not about. I put this slide last night because when I was reviewing some documentation, I felt like, oh my God, there is so much that can be discussed, so much that can be presented. But going into details of garbage collection tuning, advanced tuning, GC threads and young generation, old generation, new heap ratio, all of those things that each garbage collector will have its own 15 flags to tune, that is another presentation. There's another talk. I don't have the expertise for that. I will share you right away. There are so many other great Java professionals that have written dozens of books and articles. They are much, much better at that topic. But what I intend to share with you, hopefully, opens your eyes to what can be done. What are the possibilities? And even perhaps in a way that you don't have to dig into advanced garbage collection tuning, just enough. And if that is enough for your performance goals, then great. If you need way more, then please go read those Java performance tuning books and talks from other amazing Java professionals. All right. I'm digging into it already. I never done a deep dive, so please, bear with me because I have no idea what I'm doing. Jvm D4 Ergonomics. Here's what I like to say. I like to say that Jvm Ergonomics, we like to say that don't do premature optimization. Well, ergonomics are premature optimization. In a way, there's always an optimization. Even if the objective of that optimization is to be conservative, so that the application has just enough throughput and enough latency. It's not the throughput is not too high, the latency is not too low, and the application starts and runs. And that is the intent of D4 Ergonomics, to get the JVM to run in almost any case with any application. But that is almost never our intent as professionals, as developers. Our intent is always to get highest throughput with the lowest latency possible, with as little cost as possible, especially if I'm running in the cloud. But understanding that D4 Ergonomics are some sort of premature optimization is important because it will keep you awake. It will keep you in a state of alert that if you're deploying things or somebody near you is deploying things to production, relying on D4 Ergonomics, that's a sign. That's a sign that something is probably not going as good as it could be, especially if running on Kubernetes and containers. All right, so I want to start this conversation with you. This is a conversation, it's a deep dive, but also a conversation, especially the first part. I ran this poll on the internet early last year, and I asked how many garbage collectors are available on a usual vanilla OpenJDK 11 plus distribution. And those were the votes. There's no, the blue box doesn't mean that's the right answer. I will show other questions from the same poll, 5 questions. The blue box is the most voted one from folks on Twitter. So it doesn't mean that's the right answer. I'm going to put an arrow showing the right answer. But I want to ask you here, who believes there are only 2 garbage collectors in the JDK? Raise your hand. Who believes it's 3? Okay, a few hands. Who believes it's 4? All right, more hands than 3. Who believes it's more than 4? Okay, and raise your hand if you didn't raise your hand before. All right. You can take a guess. That's the idea here. The right answer is more than 4. There are more than 4 garbage collectors available in a vanilla OpenJDK distribution. And that by itself is a challenge. When I talk to my friends on the .NET side at Microsoft, it's like only 1 garbage collector. And they optimize that garbage collector. It's magical. It does a lot of things. It analyzes a bunch of stuff. And it kind of does a little bit of what one garbage collector in Java does and what the other garbage collector in Java does. But actually, I'm not sure if it's just 1. It might be 2, but definitely not as many as OpenJDK. All right, let's go to the next question. What data from the system is used by the hotspot JVM during startup time to use as criteria to select a garbage collector? Who believes it's just memory? Raise your hand. Who believes it's just CPU? Who believes it's CPU and memory? Who believes it's the size of the class path? Okay, good. I'm glad to hear 0%, not 2.3%, because that was definitely the wrong answer in the poll, just to use all the 4 boxes. The right answer is CPU and memory. Depending on how many processors are available to the JVM, not necessarily in the machine, to the JVM, because again, it may be running inside a container, right? How many processors are available for the JVM, and how much memory is available for the JVM in the system. Whatever, if the system is a host, the VM, the container, doesn't matter. Okay, so next question. How many garbage collectors do you think the JVM may consider when evaluating ergonomics? Is it a big if-else statement? Is it a big switch statement in the algorithm of the hotspot JVM? There are more than 4 garbage collectors on OpenJDK. It will look at CPU and memory, and then it will select which garbage collector. How many garbage collectors it uses, it may consider. All of the available GCs may be chosen at this stage. between 2 garbage collectors, between 3, or you don't know. So who believes it's all of them? Raise your hand. Okay. Who believes it's between 2? Who believes it's between 3? And raise your hand if you don't know. All right, awesome. The right answer is only between 2. If you look at the source code, because OpenJDK is open source, if you look at the source code, the algorithm will look at CPU and memory and then make a decision. Okay, if it's this amount of CPU or memory, I'm going to use this garbage collector. Otherwise, I'm going to use this other garbage collector. That's it. And we're going to find out later which ones are used, when, how. So here's a question I did after all of these questions. Do you trust Jvm Ergonomics? So I ask you, the audience, who will always trust ergonomics? Raise your hand. Okay. Who trusted until now? Who never trusted? And raise your hand if you didn't know about anything like this. Okay, awesome. Who would like better Jvm Ergonomics? I see hands poking, like you don't know if you want or you don't want. All right. At this stage, I will expect like a wave, like soccer stadium thing, like everybody raising your hand, you know. After that poll, we did another survey, and we asked people a little bit about their deployments. How did their deployments look like in production? We asked about 150 people more detailed questions. And of the 150, actually no, more than 150, sorry. 150 is just the summary on the left side. The main bullet here on the right side, this one here, that's the main survey. I think it was like 300 people. Out of the 300 developers, 65% were deploying no more containers with no more than 4 CPUs, up to 4 CPUs, up to 4 gigabytes of RAM. And half of them characterized their workloads as I/O intensive. There are 3 types of applications, generally speaking. I/O intensive, which can be disk or network, so I/O. CPU-bound applications that perform mathematical calculations or whatever, and memory-bound applications, analysis of like big data applications, for example. So half of them I/O intensive. Our assumption is that the majority of the workloads are microservices or web applications, REST APIs, and they therefore are mostly network connection to the database, pull data, connect to another service or microservice, pull data, and then send a response back to the user or whatever other system requested the information. So on the left side, you can see that of the 65% of people, majority of them are deploying only 2 CPUs. And then we have a little bit of like 4 CPU and 1 CPU, 3 CPU. And you can see also the classification, 49%, the yellow box, is I/O intensive, blue is memory intensive, and green is CPU intensive. And light blue on the right is, I don't know. And the amount of memory varied between 256, actually 500 megabytes, up to 4 gigabytes of RAM of containers. But we felt that this survey was kind of wonky. It didn't provide the sort of information that we were hoping for, and it also, we felt like not only the volume of the survey was not great, the details provided by the people we believe was misleading. Even they didn't know exactly. So we spoke to New Relic in a partnership with New Relic, and they shared this awesome dashboard with us. What this dashboard shows is data from roughly 10 million JVMs monitored by New Relic. And they shared information with us, like, is the JVM inside a container? And that's on the top left over there, 62% inside containers. Most of the JVMs monitored by New Relic are inside containers. Then they also share the version of the JDK running inside a container. At that time, I think this was data from late 2020, and the majority was still in Java 8, followed by Java 11, 8 with 61%, 11 with 33%, and 17 was still not showing up. The other information that we got was number of CPUs for the container. And look at that interesting data point, only one CPU. The majority of the JVM workloads deployed inside containers were being run with only one CPU. And we're going to see the impact of that throughout this deep dive. What else is interesting here? We ask how developers are configuring the heap size. 72% are using a hard-coded flag, XMX, the one that exists since ever, and only 8% are using the new flag, max run percentage. Only 6% of those Java workloads had advanced garbage collection tuning configuration, like the number of GC threads. And that is to show how many people are actually tuning the JVM. They're not. They provide basic information, like I want this garbage collector and this amount of heap size, and please do the rest. How much memory? What is the max heap size? You see the majority, no more than 1 gigabyte of RAM, and followed by 2 gigabytes of RAM, and actually followed by no setting. And that is to me the interesting part. Like 27.64% did not set a heap size, which means they are relying on the Jvm Ergonomics to provide the heap size. And you're going to see how funky the full heap size is on the JVM. And on the bottom here, we see information about which garbage collector is in use. Of the JVMs that have an explicit configuration, of the JVMs that they were able to identify, 65% were relying on, were unconfigured, and 25% using G1. I think this chart here, this is the one that we asked them later, and it's this screenshot is an old screenshot. I think this one is not accurate. The accurate is on the right side, because there is a mismatch here. Yes, on the right side we see 54% using G1, 31% using parallel. And the reason 54% are using G1 is because developers were setting the garbage collector in the JVM flags, like -XX plus use G1 GC. And how the other collectors were being used. So let's dive into a quick quiz here. I'm going to run a series of commands on a command line. I'm going to set the memory of the container. I'm going to run it, and you have to guess how much memory the JVM will allocate for the heap size for that JVM. As soon as I reconnect to my code space. And one of the reasons I've been using code spaces for this demo is because all of the settings in Kubernetes and kubectl, and I have this environment configured, and hopefully it stays live, and I can just go to the shell and kubectl get pods, and yeah, there you go. So it's still connected. Okay, so let's go into the task ergonomics. So I have a shell script that will store a Docker container within a certain amount of CPU and a certain amount of memory. And you have to guess how much memory will the JVM allocate for that container. Okay? sh test one CPU with 128 megabytes of RAM. Okay, this test will actually show which garbage collector is selected by the JVM and how much memory will be allocated for the heap size once I run this command. So who wants to take a guess on heap size and garbage collector? Raise your hand. Okay, yes. 64 megabytes of RAM for the default heap size. And which garbage collector? G1? The serial GC? Okay, so you're betting on 64 megabytes of RAM and serial GC. Anybody wants to bet with him? Who wants to bet with him? Raise your hand. Who wants to bet against him? Okay, gentleman over there, two gentlemen over there. Yes, you. What is your input? Sorry, one thing to clarify. This is JDK 17, just in case you actually know details about the JDK version. So can you please just speak louder, please? G1? Not G1. CMS or parallel, okay. And heap size? I would say it would start at like 40 or 50. 40 or 50. Okay. You want you want to change your guess? Okay. Which garbage collector? Sorry. Okay, so I'll just keep your initial bet because clearly you're bad at changing your bets. All right, so let's run this one. So it will create two containers. There you go. So we got max heap size, 67 million bytes, which is 64 megabytes, and use serial GC. True. So you got it right. Well done. You can take these numbers here, 6710, and put in the lottery because it may be worth something. All right, let's try a new one. This one is good. Let's go with 2 CPUs and 1 gigabyte of RAM. Who wants to take a bet? We already have a winner. You cannot bet again. Who wants to take a bet? Raise your hand. 2 CPUs, 1 gigabyte of RAM. What is a garbage collector? And how much heap size is allocated? Yes?
I'd say 512 megabytes of heap and the G1 GC.
512 megabytes and G1 GC. That's your bet. Anybody wants to bet against? Who wants to bet with him? Raise your hand. Okay. Who wants to bet against him? Yes.
Parallel and
215. 256. All right. So we have one gentleman. I need to improve my lottery game here. So bet 1. Actually, bet 1 and bet 2. All right. Sorry, what is your name? Bet 1? Niels? All right. I don't know how to spell that, so I'll just write in Portuguese. Niels. Almost. And you? Ivan. That's easy. All right, so let's run this one. 2 CPUs and 1 gig. Ooh, look at that. No one got it right. It chose the serial GC and 512 megabytes. So, Neo, you got that right, but the garbage collector is serial GC, not G1. But you got 50 points of 100%. Let's give it another shot. And then after I show this last one, because this one is tricky. I have 2 more for this, and these are the tricky ones. It's 2 CPUs, 256 megabytes. Is it 256 megabytes? Yes, I think it's 256 megabytes. Actually, no. Let's do 400 megabytes. Yes, that's the tricky one. 2 CPUs, 400 megabytes. Who wants to bet? Ivan is like, not Ivan, sorry, the other guy, the first one, the winner. He's like this. You want to bet or not?
I can guess, like, I would say it would be against serial and
256 meg?
yeah, or some with
Okay. Who wants to bet with him? Okay, very few hands. Who wants to bet against him? Yes.
I would say 128.
128. Bet 2, 128. And which garbage collector? Serial GC. All right. All right. So, for 400 megabytes, the heap size is, I don't know how much is this in, $200 megabytes. But if I run with 1 CPU, it's still the same? That's not what I saw before. Wow, this is not what I saw before. Trust me, believe me, you gotta believe me. This is not what I saw before. 256. Okay. But if I go for 300, yeah, little bastard is tricking me. I swear to God. Because I did this morning. I put in a spreadsheet. You gotta trust me. See, there's a spreadsheet. I did this thing this morning with a spreadsheet. And it's tricking me. What is the amount? 448. 448. Oh, don't start with YAML. No, this is not YAML. This is just a Docker run. Wow. What happened in my system? Well, here's the lesson. The lesson stands. You don't trust Jvm Ergonomics. That is still the lesson here, okay? Because clearly, I swear to God, I ran this test before. I may have done something with memory, like I freed memory on code spaces because it started again. I don't know what happened. But yeah, clearly, this is not what I ran earlier. So yeah, it's nothing. It's memory, -- memory, CPUs. Oh, stupid. Jesus.
You rigged the test.
I rigged the test. I was cheating. I wanted you all to get it wrong, including myself. Yes. Okay, so let's do this again. So the amount was 400, right? Yeah. So let's run this again. Okay, so that's the heap size. The default heap size is 128 megabytes. So you got it right. And the garbage collector is a serial GC. And finally, the last trick is this one. If I run with 2 CPUs and 2 gigabytes of RAM, which garbage collector, how much heap size? Who wants to bet? This is the last one. 2 CPUs with 2 gigabytes of RAM. Yes?
0 and G1 and 1.5 gig.
1.5 gig? 1.5 gig with G1. Who wants to bet against? All right, yes.
No, that's way too much. I would say 1 gig at most. Maybe more like 512.
Okay, bet 1 is 1.5 gig and G1, and bet 2 is 1 gig most. And which garbage collector?
Yeah, the same.
G1. Okay. Nope. Both got it wrong. It's 512 roughly megabytes of RAM, but it is a G1. It is a G1 GC. And the last one is this one. Two CPUs, but only 1,791 megabytes. Which one? How much heap? Which garbage collector? This is the last one. Who wants to bet? Who does not want to bet? All right, the gentleman who already participated, help me out. Just take a guess. Yes. 512. Bet 1. 512 with G1. Anybody wants to take a guess on bet number 2? Yes. Serial with 500. All right. And we got less than 500 and serial GC. So anybody wants to take a guess, what is the trend here? No? Yes.
looks like you get 25% of the memory. With the large memories, you get 25% of the memory allocated.
So with large memory, you got 25%, and with low memory, 50%. Okay. Okay, so lesson here is that high memory, actually large memory, 25%, small memory, 50%. All right, cool. Keep that in mind. So one CPU, here's the lesson. Here's one lesson. One CPU, always serial GC. Doesn't matter how much memory. One CPU, always serial GC. 2 CPUs, you have to have at least 792 megabytes of RAM. It has to be 1,792 megabytes of RAM. And why is that? Because somebody in 1998, or God knows when, wrote on the OpenJDK source code, if the system has 2 gigabytes of RAM, don't mess up with 256 megabytes of potentially reserved memory for the graphic card. And that is a threshold. That is the code. There's a block of comments this size, like 10 lines, explaining why they went with 1792 as the divisor. So the trick now with this lesson, 25% and 50%, is this. If I run, now it doesn't matter the garbage collector, will always be serial GC because I'm going to do with one CPU. But if I do 256 megabytes, I will get 128 megabytes, which is, give it a take, 50%, right? But if I do 500 megabytes, do I get 50% or 25%? 50. Nope. You get 128 megabytes. It's a non-linear calculation. There is a reservation in the ergonomics that is like, okay, make sure you have, before you jump to 25%, you keep some room. And which is why I put on that spreadsheet, because it will give us this nice chart. Oh, I forgot to put an animation to delete the quiz. And let's bring this front. So what you can see on this chart is that from 64 megabytes up to 256 megabytes, the default heap size is 50%. But somewhere between 256 and 512, the default is something like 127 megabytes, always. Only after 512 megabytes of available memory in the system, the default ergonomics of the JVM, we start calculating using 25% as the default. So if you're relying on JVM ergonomics to set your heap size, don't. Go to your configuration, change the flags, and don't rely on JVM ergonomics. Because if your ops team is adding more memory to the pods without your knowledge, they might be reserving memory in your Kubernetes cluster for that pod without necessarily reflecting in the heap size of the JVM. They would hope the JVM would pick it up, but it does not. So you really have to know about ergonomics if you're not tuning the JVM by yourself. Who liked this? Awesome, thank you. Appreciate it. Now, there are a few things in OpenJDK. As any software, it contains bugs. And those bugs, not only D4 ergonomics are tricky, when there are bugs, it's even worse. Because you try with OpenJDK on Docker on your local computer, but it's using cgroups version 1. And then it deploys on Kubernetes in production, and it's using cgroups version 2. Or even worse, in your local environment or in your staging environment or testing environment, I don't know, you're using containerd, but in production you're using podman. The behavior might be different. So these two bugs are very good examples of this. The first one, it's a bug in cgroups version 2 that impacted JDK 11. It got fixed on JDK 16 and got backported to JDK 11 because JDK 11 is widely deployed now. So it got backported. It only got released in July this year. Until then, people were believing on something that was not actually happening. The memory limits were not being respected as expected. And on JDK 17, 11, 17, and 18, Oracle changed how the number of CPUs that the JVM will see when it runs inside a container, they changed the calculation. And we're going to see a little bit more about this later. But the message here is this: don't rely on ergonomics. Only if you know what will be the values. But still, don't. Because most likely, in a Kubernetes environment, you want precision. You want to know what is running, how is running, how much memory, how many CPUs, all of that. Because that is exactly what the ops team wants to know. That's exactly what the SRE team wants to know. That's exactly what provisioning team, the team that manages the budget, the team that manages the cluster, whatever, they need to know how much memory do you need, how many CPUs do you need, all of that. So you got to keep that in mind. And do not do Java minus jar. This will be my hashtag for the next 5 years. Do not Java minus jar. Always set a heap size, preferably with the percentage, for containers especially, and always set a garbage collector. And know how many CPUs the JVM has access to, and you're going to get to that later. Okay, so garbage collectors. Garbage collectors are tricky. The function of a garbage collector is very simple. It's about allocating memory and cleaning memory. Allocating objects into memory and cleaning objects from memory. And moving objects as they remain old, and put them over here because they are old and they have lots of references, so you stop running by them, and you keep collecting mostly the young objects, not the old objects. Once in a while, the garbage collector will look into the old objects. Oh, you're still there? Oh, Jesus. And then remove it. Young ones, just mostly will clean up right after. What happens with a poorly tuned garbage collector? The application will have high pause times. The application will have a certain amount of percentage time spent in those pauses. High number of pauses, and then long pauses. Starvation of threads, because for the garbage collector to run, it needs threads, system threads. And if there are certain amount of memory is being occupied and the garbage collector cannot operate, it will trigger out of memory error, because the memory is totally full, I cannot work, and there's no way to work on this environment. So it triggers an out of memory error. Why GC tuning is important? Because it can allow you to save costs. It can allow you to run your system with the existing infrastructure, with the existing resources that you have access to for your system. The amount of nodes, the amount of CPUs, the amount of memories in an environment, whether it's on premises in your own data center or whether it's in the cloud under a certain budget, it allows you to do more with the same. Or it allows you to do faster. It allows you to deliver better experience. It allows you to stay on time. There are a lot of benefits, but cost is one of them. I have a friend who worked at Twitter, and he said we tuned the JVM engineering team at Twitter. They optimized a bunch of their applications, and they were able to save 5% in cloud infrastructure. 5%. Does it sound not enough? That represented like $7 million per month in cost savings, just 5%. So there is a lot of conversations about what you can do with tuning that not only is about delivering a better performance for your end users, but also saving costs. But setting the heap size is not enough. What you really want is to select the right garbage collector. You want to make sure that the application has the right amount of CPUs or enough CPUs to do what it needs to do. And this is critical. For any performance tuning exercise, you have to have an objective. Is your objective 5,000 requests per second? Or is your objective P99 latency of no more than 10 milliseconds? You have to set an objective. You have to set an SLA. Or maybe it's the percentage of the CPU, but usually that's not the goal because that's not business. The consumption of the CPU is a reflection of a bunch of stuff. And you should look at that as a signal that your system is not doing well. But your requirements, SLA requirements, are more business focused. So what is a heap size configuration? What can I do to configure my heap size in a way that scales better, performs better? As we saw in these examples, the default heap size is not linear because of the way ergonomics work to be conservative and good enough for most systems. But what we, Microsoft, suggest for customers that are deploying Java inside containers in a Kubernetes environment especially, but doesn't matter if it's Kubernetes or not, is to, if it's not a container, you have to configure the heap size to whatever the application needs. Oh, it's Kafka. Well, Kafka needs memory. It's Cassandra, it needs memory. It's Hadoop, it's Spark. Those big data systems, they will come with their own requirements. And it's really about the volume of your big data and whatever you need to do. But if you're running microservices in containers, our suggestion is 70, 75%. And you can configure this heap size using the max run percentage flag over there. You set to 75, and if the ops team looks at the telemetry and like, oh my God, this system here is not performing well, clearly the pod has memory available, the node is not fully committed, there is memory, the ops team can go and increase the memory of that pod, which in turn will give more memory to the container, to the JVM, and restart the pod, the JVM scales along with it. Now, there is an interesting thing. If you have a small container and you set 75% or 80% or 90%, what happens is your off-heap memory gets smaller. And the smaller the off-heap memory, certain applications may not operate, including the JVM itself. Some garbage collectors use off-heap memory to have data structures as part of their execution to clean up the heap itself. So, for example, G1, if you set a container with 256 megabytes of RAM and you set G1 GC and you allocate 90% of that container to the JVM, the application, the JVM will crash because the G1 GC needs off-heap memory to operate. So you have to be careful with that percentage. But the tricky part is the bigger the amount of, the more memory you allocate to the container, the higher can be the percentage. Because if you, let's say you have a big data container and you allocate 40 gigabytes of RAM to that container. If you allocate 70%, that still leaves a lot of memory for off-heap. So you can actually increase the percentage to 85%, sometimes to 90%, because the off-heap is still large. So the percentage is not also like golden rule, but it's a good starting point for most cases, most scenarios, especially the ones that we saw in the beginning where it's small container, small memory, small CPU, IO bound, microservice, REST API kind of thing. Okay, so working with Monica Beckwith and Kirk and Martin and other folks on the Java engineering group, we came up with this table that shows roughly what garbage collector to be used, when, how much memory, how many CPUs, things like that, for what kind of workload. And what is the overhead for that garbage collector? Serial GC is pretty simple. It's for a computer environment with a single core. It's best for small heaps, and which is like no more than 4 gigabytes of RAM. The thing with serial is this. I mean, I guess parallel GC also does a stop the world thing. But because it's parallel, it will run multiple threads using multiple processors, and its algorithm will prioritize certain regions of the heap. The serial GC doesn't do something like that. It is just like stop the world, clean up, continue. Stop the world, clean up, continue. So the pause times of serial GC, when they happen, it can be large, especially the more objects are created. So for batch applications, for command line interfaces, you're running a command line interface. You wrote a program using Quarkus or Pico CLI and whatever library for a Java-based CLI. Serial GC is actually good for that because the application will most likely not allocate that many memory. It will execute and exit, execute and exit. So you don't need You actually don't need a garbage collector in most cases. You can use epsilon GC, which is a garbage collector that doesn't collect anything. So the overhead is minimal. The application doesn't pause. There's no frequency in pauses for parallel execution because it's serial. But when it does pause, it can have a strong tail latency effect. The next one is parallel. So parallel is good for multi-threaded environments with 2 or more CPUs. Minimum overhead as well, but it can have a high tail latency effect. But it's good for batch applications as well that may need large heap sizes. Microservices, REST API, it works well. Multi-core, small heaps, that's the intent. You're running a microservice application, you can use parallel GC in most cases. G1 GC, what everybody believes is the default GC, and as we saw, there's no such thing as default. I personally like to say the default is serial GC, especially if you're running containers. The default is serial GC. If you're running with 2 cores and 1792 megabytes of RAM, then you got G1 GC, or unless you explicitly call for it. Large heaps is good for more than 4 gigabytes of RAM. It has a moderate overhead, but the overhead of both the G1 GC, all of them, G1 GC, ZGC, and Shenandoah, one thing that they are good at is expectation. You know you're going to get pause times of up to 10 milliseconds, up to 5 milliseconds. You can actually configure G1 GC for something like that. Don't pause for more than X milliseconds. I don't want to see pauses larger than X milliseconds. And then the garbage collector will work within that. It may affect throughput or it may affect latency, but that's why advanced GC tuning, it's kind of complicated and it really depends on your workload. ZGC and Shenandoah, we just felt like it's really like an exploration for the teams that are doing performance tuning, garbage collector performance tuning. Okay. I think I may have skipped a slide or two, or not. Oh, yeah. So we're going to start getting into Kubernetes stuff. So this is like a summary. Java 11 or later, the ergonomics will select either serial GC or G1 GC. On Java 8, you get serial GC or parallel GC. The real default, my take, is serial GC. The environment needs 2 processors or more, 1792 megabytes or more to get one of the other 2. The default max heap size, it can be 25%, it can be 50%, or it can be very close to 128 megabytes value. Between 256 and 512 megabytes of available memory, you get roughly 128 megabytes. So in the end, it depends, especially if there is a bug in OpenJDK. And now we're going to start looking into available processors. And this is important for our next part for Kubernetes. In the JDK, there is an API called runtime.availableprocessors. It will return how many processors the JVM can see. It's 1 processor or 2 processors. When you run it on your laptop, on your bare metal laptop, on your actual laptop, not container, not a VM, you're going to see a number that reflects exactly how many cores you have in your laptop. So let's try that, and let's talk about this a little bit. So we're going to go here and create a little program. available processors.java. Giving me method main showing available processors. And that's GitHub Copilot. So now I'm going to click Run. And this will show four processors. This is not my laptop. This is running on GitHub code spaces. So it is, in a way, it's a container in cloud. So if I go to github.com/my username, and I go to your code spaces, we're going to see here, this is the code space I'm connected to, Miniature Pancake. And it's a 4-core machine with 8 gigabytes of RAM and 32 gigabytes of storage. So on this environment, I get 4. Now let's run this thing on my local computer. Available processors.java. Java available processors. Ouch. Yes, okay, Mac. Jesus. Oh my God. Yeah, my terminal wants access to my Google Photos just in case I want an auto-completion of a picture of me 15 years ago. Jesus. All right, Java, I'm going to copy and paste faster. Copy paste is always faster. Okay, so in my local computer, I have 10 processors, right? So the JVM sees 10 processors, and that's what I have here. I don't know. Task. Activity. Monitor. Window. CPU usage. There you go. So this is my CPU usage little widget. So I have 10. 3, 6, 9, 10 processors. All right. But here's the funky thing. Active processor count equals 2. I can tell the JVM that the JVM only has access to 2 processors. And boom, it will give me only 2 available processors. This information, however, does not mean that I cannot run multiple threads at the same time on more than 2 processors. And that's the tricky part. This information is only useful for the creation of thread pools. Thread pools used by frameworks and libraries and the JDK itself. So here's the tricky part. If the application is running inside a container and the container has only one CPU, the cgroups awareness, container awareness supporting the JDK will read that information. And instead of looking at the host, it will look at the container, cgroups. And cgroup says, oh, yes, you only have one CPU. Okay, available processors equals 1. All right? But if the container is running on a machine that actually has more than one processor, I can override that. It doesn't matter. I can come here, and let's say I can actually do 24. Still runs. It doesn't matter. Oh, you don't see it, sorry. PowerPoint, the company that does these things. So if I override the flag, active processor count equals 24, it doesn't matter. It's just a just an information that the JVM computes so that things like the fork join pool used by the JVM, or GC threads by the garbage collector that got selected, or frameworks like and server runtimes like Tomcat or Spring or Jetty or Natty, whatever has to create a thread pool, it may use this information to size the thread pool in a way that matches how many processors are available. What's the point of having a thread pool of 2 million threads if there's only one thread? One CPU, right? I don't want to talk about Loom, by the way. Go to a Loom talk later at this conference to look into that. But that's another topic. Here we're talking about system threads and processors. But this information can be overridden, and it's going to be useful later on. By the way, we have I think we are almost ready for the break. So let me see what I have left here. Yes, so summary. Oh yes, I think I forgot to talk about CPU, and this is the beginning for the next part. So when you talk about Kubernetes and how many CPUs and how many CPUs or cores are available to the container in a particular pod, usually that configuration is through something called millicores. You set how many millicores will be available to this container. And usually 1,000 millicore is seen by the JVM as one processor. 2,000 millicore is seen by the JVM as two processors. But the range of 1,001 millicore up to 2,000 millicore is two processors. And there's a big difference between 1,001 millicore and 2,000 millicore. There's a huge difference. There's a difference of a CPU, basically. And this is important because when you're going to talk about CPU throttling, I'll give you the hint. Kubernetes, your application, when it runs a multi-threaded application running on Kubernetes, it always has access to the other processors. Always has. Your limit may be 1,000 millicore. It doesn't matter. You can still run 30 threads, and those 30 threads, if the machine has 30 cores, it will run at the same time. But if the millicore configuration is 1,000 millicore, what happens is the application will consume that CPU time limit very fast, and the application will get throttled. So I want to pause here, and we're going to go for a break of 30 minutes. And if you have questions, you're more than welcome to come here, and we can look into code and whatnots. But let's get back here at 11:15. All right? Thank you very much. All right. Let's get back to it. Welcome back to those who returned. Welcome to those who joined now. Who did not watch the first part? One hand, 2, 3, 4, 5, 6, 7, 8. Nice crowd over there. Welcome. Thanks for joining. So you came for the best part. A lot of YAML. A lot of it. Too much. Please help. Call 911. What is the number here in Belgium? Is it 911? 112? 911 also works. Thank God, because I'd be like, please pick up, please pick up. It is also 911 in Canada. Not in Brazil. Doesn't matter who you call in Brazil, it doesn't work. That's why I moved to Canada. All right. So I'll recap, and especially for the folks who just joined. First part, we talked about JDK ergonomics, D4 ergonomics. We saw how you cannot trust them, how the values are moving targets. It's not like it's 25% always heap size, default heap size. It's not always 50%. We saw that the default garbage collector is actually serial GC. And please, if you have Twitter, tweet that. Hashtag DevOps, serial GC is the default. Bruno said, don't blame me. That's your quote. And what else we saw? We saw that Bruno doesn't review his shell scripts before doing the demos, clearly. We had a great game. We had clear winners. Thanks for participating. And what else did we see? D4 Ergonomics. Oh, yes. Do not Java-jar your app. Do not do this in production, okay? If you're doing this thing in production, most likely nobody knows what's going on. Nobody knows what is the heap size. Nobody knows what is the garbage collector. Nobody knows what is going on with your app. Always configure your JVM. What else we saw? We saw this cool table about garbage collectors. And that is it. So let's get into it. Java on Kubernetes. Let's get right into it because I have lots of demos and explorations that I want to do with you live. A lot of things will break. You're going to have to be patient. Like, oh my God, Bruno, it's taking too long. Yes, that's the idea. We're going to do benchmarks live and see results. But before we do that, we have to go through a few slides to understand why Kubernetes is complicated for performance tuning, resourcing, planning, cost, all of that. So let's first start with CPU throttling. CPU throttling is that thing that everybody talks about. Nobody understands exactly what happens when, how. Sometimes you see nice Prometheus charts and Grafana charts and, JFR here and charts over there, charts everywhere. You got a chart, you get a chart. Nobody understands what's going on. But CPU throttling is basically, actually, before CPU throttling, let's go over a recap. CPU requests on Kubernetes are for CPU time, okay? 1,000 millicore does not mean one processor. If you're setting on your YAML file, request limit 1,000 millicore, and you write a comment, allocate only one CPU for this application, that comment is wrong. You're not reserving one processor for the application. You are reserving the time of one processor. But what happens when you run two threads at the same time? They will consume the CPU time in half the time. Okay? 1,000 millicore means the application can consume a full CPU cycle per CPU period. 1,000 millicore allows an application with multiple threads to run in parallel. You still can run an application with multiple threads, even if the limit is 1,000 millicore. Even on the JVM, even when the JVM sees one processor, as we saw before, active processor count is equals 1, that flag still doesn't matter. You can still start two threads, run them at the same time. When all threads combined consume 1,000 millicore in CPU time, the application is throttled, which means whatever is left in the CPU period, the application will not execute and wait until the next cycle. So let's look at this example. There's a Java application with 3 threads. Thread A consumes 400 millicore. Thread B consumes 500 millicore. And thread C consumes 100 millicore. How many millicores were consumed? 1,000 millicore. but they all executed at the same time. The longest took consumed 500 millicore, which is half the CPU time. Now the application only has to wait the same time as 500 millicore, which is half the period, CPU period, half of it, until the next cycle. I have a nice animation here with very advanced PowerPoint effects. We're going to see how that works. But the important piece is all Java applications are, in general, multi-threaded, even if the application is running on a single processor. Concurrent GCs will have their own threads: parallel GC, G1, Shenandoah, ZGC. Web applications, if you're running a web application, definitely you're going to have threads. Spring Boot, definitely threads. Spring Boot application, Quarkus application, web application, I mean. Whatever framework you use for web, REST endpoints, gRPC, there will be a thread pool somewhere with multiple threads. Database connection pools. Are you using Hibernate? Connection pool. Are you using Juke? Connection pool. Are you using whatever, MyBatis? Connection pool. So by default, whatever you do in your Java application in general will have more than one thread running at the same time, even if you're running on a single processor. And that is true on Kubernetes. The thing with Kubernetes, though, is that if you set 1,000 millicore and you're running multiple threads, most likely your application is being throttled. Most likely your application is getting these little pauses every CPU cycle, not every CPU cycle, but enough that eventually you can observe that over time. The way the JVM computes available processors is give it or take this calculation. Up to 1,000 millicore, it sees one processor. 1,001 and 2,000 millicore, two processors. So on and so forth. You can trick the JVM. You can use active processor count, and you can say active processor count equals to 2. Doesn't matter. What matters is that information will tell the JVM and all thread pools that may get created over time within that application, it will use that information. And I'm going to create a thread pool with 2 threads because I see 2 processors. Wherever framework may have that algorithm created like that. So how does CPU throttling works? So here we have a Java virtual machine, and we have a node on my Kubernetes cluster with 4 processors. You went on your cloud dashboard, created an Azure AWS, Google, doesn't matter. But hopefully Azure. You create a cluster, and you say, give me a node pool with this type of VM. And the type of VM is a 4-core, 8 GB of RAM VM. And that is part of your node pool. So this is the image of a node running on your Kubernetes cluster, which is a VM. A node is a VM. 4 CPUs. At the top, we see the configuration for this pod, actually this container, and the default CFS period, not the default, whatever. This is hypothetically 100 millisecond. Hypothetically, the CPU cycle is 100 millisecond. It's not, but hypothetically, we're going to assume that. So the CPU limit applied to the container is 1,000 millicore. You think it's one processor? It's not. Actually, 4 HP requests come in and get executed by that thread pool that had 4 threads open. It executes and goes back. Now, each request consumed 200 millicore. That's the time to, it did like, like some prime number calculation or hash or whatever image processing, whatever it had to do, it consumed CPU. By the way, if the thread is not doing anything with the CPU, it's not consuming the CPU. It has to be doing something with the CPU. If it's waiting for the database to return some value, it's not consuming CPU time. Those requests, HP requests, they did consume 200 millicore, which means Now this application only has 200 millicores left. Because 4 threads times 200 millicores is 800 millicores. The limit is 1,000. And now this application only has 200 millicores left, but still 80 milliseconds until the next CPU cycle. But this is a JVM application. For some reason, the garbage collector thought, oh, I need to clean something. And it executes. Some GC thread goes in, do some work, cleans up the memory, and now the GC work total combined consumed the remaining 200 millicores. But my application, and that consumed that took 20 milliseconds. Now the application doesn't have any CPU time left. So what happens with those 2 other requests? Those 2 other requests will get throttled. They cannot be executed by this application because CFS put this application on standby because it doesn't have any more time left. Which means those HTTP requests will get into that latency, tail latency thing that we see in those charts, performance monitoring charts, the tail latency, where the latency was unusual. And that affects your performance goals, P90, P99, or whatever you set that you want to see latency within that scope. Those requests will get into that. And those requests will have to wait at least 60 milliseconds to execute. And that's where the CPU throttling impacts the latency of your application. May also impact the throughput, but it's mostly latency. So when we thought about like how developers are mostly doing containers and JVM and deploying that to containers and on Kubernetes and how they configure the JVM, generally speaking, we thought, what if we could provide some guidance so that developers don't have to rely on ergonomics, but also don't have to do advanced performance tuning even before putting something in production. Because sometimes it's a new system. You don't even know the performance requirements. You just need something to be live. You know, I may have 500 users, 5,000 users. I don't know exactly how many in the beginning. I just need to be live. The application needs to go to production. So we thought, okay, if your application has 1,000 millicore, we do suggest to tell the JVM use active processor count equals 2. The reason for that, and this is perhaps the most complicated part of this chart, is I'm telling the JVM can see 2 processors. So it will size thread pools based on that information. So it means it will have more threads in those thread pools than if it was only 1 processor account. And the reason for this is because for most applications that we observe deployed on containers are microservices, and microservices are, in general, mostly I/O bound. They don't consume too much CPU. They're mostly just waiting for network I/O, database requests from the database or to the database, and just waiting for things. So you can actually have more threads than usual, but not too many. And we don't recommend 2 small heaps or 2 large heaps. In fact, just go with parallel GC, somewhere between 2 and 4 gigabytes of RAM. So there is room in the heap for the application to run without frequent garbage collection pauses. What we actually suggest as a starting point instead of ergonomics is to use 2,000 millicore and select either parallel GC or G1 GC. And the garbage collector will be mostly based on what heap size you believe your application needs best. So if it's up to 4 gigabytes, parallel GC. If it's more than 4 gigabytes, G1 GC. And then there is the 4,000 millicore limits and others. It's really unexplored territory, not really part of this exercise, because if you believe you have a Microsoft that needs way more than 4,000 millicore, you probably know what you already you probably already know what you're doing. So it really doesn't matter what is a better starting point. But again, these are suggestions. It's not like you have to go with these. I'm saying that, or we are saying that you can go with this at the beginning if you have no clue, but only relying on the D4 ergonomics of the JVM for a container-based deployment of a microservice on Kubernetes, those D4 ergonomics may not be the best. And this starting point may be better for most workloads. So the other thing when we deploy to Kubernetes is something called scaling. When we deploy things to Kubernetes, we expect that we'll be able to scale out horizontally. And that is awesome because one day you may have only 500 users, the other day you may have 5,000 users, the other day you might have 50,000 or 5 million. You don't know. So you want to be able to scale out and grow accordingly to the needs of the business. The thing that we have found is a lot of customers are only relying on horizontal scaling to increase performance. And the funny thing is, I love when we see, and by the way, this also happens with Microsoft, but all vendors. We see these keynotes at conferences like, oh my God, this system has 500 transactions per second, 500 trillion transactions per second. Well, if you put 5 million computers on a data center, you are able to do that amount of requests per second because you have the amount of replicas is so big that you can have 5 trillion requests per second. The real question is, how many transactions per second per instance? That is the interesting question. Can one instance of your application hit 5,000 requests per second, 50,000 requests per second, 5 million requests per second? That is a real question. The aggregation, yeah, not so. I mean, sure, it has some business value. You're doing a lot of business, but the system may be expensive to do that. So when it comes to cost and scaling, I put this together to show the importance of properly sizing and configuring your application and your cluster. In this slide, we see an Azure Kubernetes cluster that is what I call short but wide. It is a 6x4, 24 vCPUs total, 6 nodes, and each node 4 vCPU with 16 gigabytes of RAM. The total cost of this cluster, no matter if you are running anything on it or not, doesn't matter. Just to provision this cluster and have it running, it's going to be roughly $840 per hour. No, per month. Yeah, per month. Not per hour. Yeah, there you go. It's 0.192 cents per hour per VM. So times 6 times 30, roughly 840. So that's the cost of this cluster. Now, one day you think, oh, I'm going to deploy this Java application and I'm going to deploy initially only 2 replicas. It's going to be a microservice. I'm going to put 1 CPU, 2 gigabytes of RAM. Well, when you do 1 CPU and 2 gigabytes of RAM, I want to hear everyone screaming, which garbage collector do you get? Oh my God. On 3, okay? Which cereal do you, which cereal do you get? Which cereal? I got crunchy cereal. Which garbage collector do you get? Cereal, thank you. 1 CPU, 2 gigabytes of RAM, you got Serial GC by default, okay? So you start this application in production on a cluster with 6 nodes, but you start with only 2 replicas, and you allocate only 1 CPU, 2 gigabytes of RAM, sounds reasonable. One day the system needs to be scaled. You go into the console and you do kubectl set replicas equals 6, boom, you got 6 replicas, 1 per node, and then the next day you feel like, oh my God, I need to scale even more. What do? Set replicas to 18. But you're still running those replicas on the same 6 VMs. So now, what you have is 18 JVMs replicas running on 6 nodes. You have 3 JVMs per node of the same application. Is that efficient? It doesn't look like, because you have 3 JVMs running with very limited CPU, with very limited memory, and still doing to do things that they have to do no matter what. So what are the problems? Concurrent parallel GC won't be effective because it's serial GC. You have only one CPU, generally speaking. You will get constant CPU throttling on each JVM if this system is getting bombarded by those requests. And you got constant stop the world, so your tail latency will suffer, and you're not gonna hit your P99 targets if that's what you're looking for. So you got a high latency and probably low throughput. So why running 3 instances of the same application on the same VM is a problem? Because the application is not consuming the resources efficiently or even effectively. If we look at, for example, this is just an example, the meta space of the JVM. If you're running the same application, but one large JVM and one small JVM, the meta space is most likely the same size. So what happened when you're running 3 instances of a small JVM of the same application on the same node? You have 3 copies of the meta space. So you're just wasting memory. What would be better is to have a large JVM. So we took this concept and we did some benchmark. And this is what we learned. Anybody here is colorblind? A few folks? Okay, I'm going to describe the lines and the bars, so bear with me. It's tricky. Pay attention. The very tall, the first line from left to right, the first line is green, just so you can maybe learn new colors. I don't know how it works. I don't know how color blindness works. But that's green, whatever colorblind people see. That's green, and that's the latency. So we can see that the latency is very bad. You know, even like with 90%, the latency already goes to 60,000 nanoseconds or microseconds. That's 60 milliseconds, I think. 60 milliseconds. Even before P90, it already hits the 60 milliseconds mark. By P99, it's already on 80 to 90 milliseconds. And then P99 goes all the way back to 100 more than a minute. So that's the first line. The bars, the first bar, is the same workload, the same benchmark, and shows throughput. Total requests in 10 minutes, and that's 2.5 million requests. That's the amount of total requests, 2.5 million. So we see that the first benchmark, bad latency, bad throughput. Guess what the configuration is? 6 replicas, 1 CPU. Now let's look at other examples. Let's go with the red, which is the second bar, and the very line at the bottom, very close to the x-axis, very, very parallel to the bottom of the chart. That's the red line, and the second bar shows the throughput of the same benchmark, same application, but running with 2 containers, 2 replicas, 3 CPUs each. I have the best latency, and I have the best throughput. Same benchmark, same amount of memory, same amount of CPU, total, aggregated. But I reduced the number of replicas, and I increased the resources per replica. The application is performing much better now. It's performing so much better that the latency, could easily, keep like that forever. And the throughput, 3.5 million, another million of requests total. That's more than, I don't know, my math sucks, maybe 30%, 40% more. The orange bar, which is the second line from the bottom, shows another exercise, which is 3 replicas with 2 CPUs. So I increased the number of replicas just a little bit and decreased the amount of CPU just a little bit. You can see the impact of in the latency, but not much impact in the throughput. But why the latency got impacted? CPU throttling. I mean, clearly, the throughput is okay, but the latency went bad because now more pause happened by that application in a larger percentage of those requests. But it was still able to process a lot of requests. So with the red and the yellow, or orange, see, maybe I am colorblind. With the red and the orange, we were able to improve the performance while still consuming the same total amount of resources, CPU and memory. The last bar and the third line from the bottom, the blue bar and the blue line, shows 2 containers with 2 CPUs. I reduced the number of replicas from 6 to 2, and I reduced the total amount of CPUs to 4. So now I have less CPUs and I have less replica. But I have better throughput and better latency. Which means with this configuration, I was able to improve the performance of this system and reduce the cost. Because now I have resources available in my cluster to do something else. Which means I don't need to get an extra VM in the cluster to provision another system. I can use the leftover. So what we suggest here is, hey, maybe what you should have is a tall but narrow Azure Kubernetes cluster. Have bigger VMs so you can have bigger containers and have fewer replicas. Still not 1, maybe not 2, because you want resiliency. You want to be able to do a roll upgrade. You want to be able to recover the system without being 100% fully downtime. So you want to have some replicas around, but not 20 replicas of the same system. I did see, there was this food delivery app in Brazil who decided to migrate from Java to Rust. And one of the reasons they gave was performance. And on the blog post, they said our Java system was deployed with like 20 or maybe 10 or 20 replicas of 1 CPU JVM. So they decided to go for a migration to a whole different stack, a whole different language, because they couldn't, think out of the box and just increase CPU, increase memory, give a bigger heap size, give more CPU, and maybe just readjust the number of replicas. So if you have too many replicas for your system, reconsider, why do you have so many replicas? Why do you need that many replicas? Is it really because of resiliency? Is it 4 enough? Is it 5 enough? Do you really need 50? So think about that and how you can rearrange those resources into a much better, more efficient system, to a point where you can have the same cost, but better performance and reduce cost by that system. So the infrastructure, the cost of the provision infrastructure is still the same. But now I have 369 vCPUs available, or the time of 9 CPUs available, because this system here is enough with this configuration. So one other thing that we talk about is how do you identify which topology works best? Do I go with this topology or that topology? Well, the beauty of Kubernetes is you can actually have 2 topologies or possibly more. I'm not I'm not an advanced user of Kubernetes, but you can possibly have more topologies. This is like a classic A/B testing, but I call it A/B performance testing. So I'm going to route to multiple topologies where one is smaller JVMs with more replicas, which is what most people are doing these days. And we have the new topology, which is larger JVMs with less replicas. And then you monitor those applications in production. You give different labels to the instances, and then you see which one is performing better. And then maybe that can give you a much better indication of what works best for you. So now is the part where we have 43 minutes left, and we're going to do some benchmarking exercises and a lot of YAML. But before I go into that, anybody has a question? Yes? When I talk about CPU, I talk about millicores? Yes. 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 There was another question here?
Is it really somehow correlates this millicores to time, or what's the way to somehow metric it?
That's one thing I still don't get completely myself, the correlation between 1,000 millicore and CPU period, because the CPU period is a configuration that Kubernetes has a default, CFS. And in some systems, it may be a millisecond, it may be a 10 milliseconds, I don't know. But there is a CPU period. And 1,000 millicore represents the full CPU cycle within that period. The 100% of CPU time within that period. So let's say a period is 10 milliseconds, and I set to 500 millicore, and let's say 1,000 millicore matches that CPU period. If I only give 500 millicore, I'm giving half the CPU time within that period. So if the thread consumes 500 millicore, that means half of the other period cannot be used because I only allocated 500 millicore. All right, so thanks for the questions. Let's go into some YAML. So I'm going to reconnect to the code space because every time my laptop goes on standby, it disconnects. All right. So let me just walk you through quickly on this Java application. It's a Spring Boot application. Who is using Spring Boot here? Okay, more than half. Who is not using Spring Boot? All right, thank you. Brave souls. Okay, so this Java application is very stupid. It has a hello world on the endpoint slash. There is a prime factor calculator under slash prime factor. And by the way, this implementation here, I copied from the internet, of course, because I'm not smart enough to do a prime factor calculation myself. So I went on Stack Overflow and I copy-pasted. The thing that I was able to do was to make it worse, because I'm really good at that. And what I did was to use big decimal for everything. So big integer, not big decimal, sorry. So all the operations are using big integer, and intentionally, because I want to consume CPU time. So I really want this application to be, this part here to be slow, intentionally. All right. This is the record prime factor, just to get a result. And what else do I have? Oh, I have the inspect /inspect. This will give me some information from the JVM, like the IP of the pod, just for my debugging purposes. Available processors, max memory, total memory, what is the garbage collector being used, and also some other information from the MX beans. And I do get a property CPU shares that I inject from my start command that we can get from here from cgroup. So I get the CPU shares from cgroup just so I know what was the CPU share informed. Anyhow, just so you have some ideas. So there is a hello world, there's a prime factor, and there is a /inspect to get detail from the JVM. Okay, so let's go play around. So first thing we do, kubectl get pods. First thing I did, I deployed the application using D4 Ergonomics. So the D4 Ergonomics configuration is this beautiful YAML file. I'm going to do a lot of jokes on YAML, where we have the application. Here's the simple application ergonomics. I have my instrumentation key for my APM agent. And I don't set any Java OPTS. So I am really relying on ergonomics on this application. And here's my limit, request and limit. 1000 millicore with 1 gig of RAM. So let's kubectl exec -ti, and I'm gonna go into the load test pod, because I run my benchmark from this pod. I have one particular pod that does the load generation. So here's the URL. And let's do, I'm not sure if I have wget. Oh yeah, I do have wget. Okay, so here's my inspect. So this application is running with total memory size of the container, 1 gig, and the GC is mark sweep compact, which I think it's serial. Max memory is 25%, 247 megabytes, because it's 1 gig, and 1 processor count. Okay, so following ergonomics, I got serial GC, I have 247 megabytes heap, serial GC, okay, in 1 processor. Now, let's do a load. And let's do this load for 2 minutes, or 1 minute. So 8 threads, each thread, 10 connections. I'm not sure if it's 8 threads, each thread with 10 connections, or 1 connection each with 8 threads. Anyways, actually no, you got 8 threads, each thread, 10 connections, yes. So let's go into the Azure dashboard, and we're gonna see these requests live metrics. There is an overhead when I do live metrics, but I want to show you. The overhead is, if we do the benchmark with, and we have the overhead in all benchmarks, yeah, there is a variation, but not big deal. Okay, so we have 6 replicas, and we're just doing an inspect. The inspect is just like get some information, create a string, JSON, serialize that, Spring Boot will return that, and that's it. So we can see the variation here. It got some peak of 10 requests. Latency was very good at below 0.5 milliseconds. But why is that? Because this inspect thing doesn't consume CPU. It's just like a JSON thing, like a hello world. But if we do the prime factor, prime factor. Actually, I don't remember the URL. Hold on 1 second. Prime factor number. Yes. So let's get a funky number here. This one. Okay. So for the inspect, we got 10,000 requests per second, and the latency was pretty good. But in here, we should get more latency variation. Or maybe not. I may need to increase the prime number, make it bigger. Yeah, let's do this number a little bit bigger. I'm gonna do all of it. So it's this number with login. And why login? Because I'm logging every iteration, so that's like creates a string like crazy. So a lot of object allocation. Oh, still no variation on the, yeah, interesting. I don't remember what number, prime number I used, but probably not this one. This is a 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, this is a small number. Let me get my tests. Test. So what? Now I have a number here that if I run on my computer, it takes 4 seconds. This one. So let me try this one first. Oh yeah, that's true. Oh. Okay, now there is some variation happening. Yep. So CPU usage also went up. Requests per second went down. Latency is varying. Yeah, latency is much, much better. Better. It's actually worse, but better to demo. CPU usage went above 50%. You see the variation because before the CPU was like a line like this, and that's because the application was performing just well. But now it is up and down. That's CPU throttling happening, and also the latency definitely shows some throttling happening because now it's taking longer than usual in some requests. And other requests per second also went bad. Okay, so we got an application here. Let me take a screenshot of this. And yeah, let me do this. Yeah, that's better. Now let's improve this system. Okay. First thing we're gonna do is not rely on ergonomics. And by the way, it may actually get worse before it gets better. And that is okay. So now we're gonna do max run percentage equals 75. Of this application. And this is the total requests per second for this execution. 1,500 requests per second. That's kind of bad. And actually, let me save this. First run Ergonomics. And we got where's the summary? This one. Latency distribution with this amount. Okay. Benchmark DevBox. So now let's go and redeploy. So we changed the YAML file. We added a heap size. And we also going to do use parallel GC. So now we're going to go kubectl, cd deployments, kubectl, apply. Oops. kubectl apply minus f deployment. Oops. So deployment kubectl apply minus f app. I'm going to actually take out this and let's first try without changing the GC, just the heap size. Replace. Okay, cool. So it's going to terminate all the 6 pods and recreate them with the new configuration. Container creating. Okay, and this font is better. And running. So let's go back here. Let's do a curl. To get that this is up and running. Come on.
I think you replaced the service, so it might have another IP.
No, it's the same IP. Or maybe not. It is the same IP. Oh, it's not. It's 10. Look at that. I told you it changed the IP address. You were not listening. Still the wrong IP. I heard somebody shushing like, Bruno, idiot, forgot to change the other number. 10.224.0.10. 10.224.0.10. Okay. You won this one. All right. Why? This is weird. kubectl Get pods. kubectl. Zach. Bash. So it is 75. So it got what we wanted. Oh, shit. So let's get back to the load test. Okay. Oh. Yeah, why? Oh, I know. The previous IP was the IP directly into the pod, not through the load balancer. That's why. That's why the IP was, that's why the port was not 80. Okay, so let's do the work again. All right, so I couldn't exactly confirm that the heap size increased. We'll see how this one goes. And okay, primary factor, the same number with logging. Okay. So, well, it appears to me that the heap is bigger. I just couldn't confirm on the inspect. But we can see the latency here now is better, which means the garbage collector is running less, consuming less CPU time. We got better requests per second and the throughput. CPU usage is still weird, but at least the latency in general. Oh, now the chart actually updated. Oh, okay. Not as good as we would hope for. It just rescaled. Yeah. No, I got it. You know what? Let me give another number here. 7.3. And let's do this again. Let's make a big number. I love the chart. It starts great and then just goes crazy. So ideally, what you want to see in this chart is steady lines. You don't want to see lines going up and down. It's the same workload, the same amount of concurrent connections, same thing happening all the time. What you really want to see is like requests per second, steady, and steady latency, steady CPU usage, except for the parts where it doesn't get steady because something is going on. It's going to scale as soon as this dot leaves the chart. Rescale. Let's see some samples. Still going fast. Less than 1 millisecond. Why is that? Let's look at the, not here, the controller, prime factor. We need a bigger number. and $40. Okay, we did it. We did it. It went from 4,000 requests per second to 1, and it took 40 seconds. That's exactly what we wanted. Look at that. 56 seconds. Wow. All right. Clearly, this demo is not working as originally planned. So let's go with another one. Okay. So I want to show you the A/B testing. That's the one thing I like, because it can show how different garbage collectors perform in parallel, like comparing two garbage collectors in production at the same time. So let's get out of here. Actually, is it work still running? No. So we get out of this thing, and then we're gonna kubectl get deployments. We're gonna delete this one, kubectl delete deployment, and we also need to delete the ingress. kubectl get services. This one, kubectl delete service. This one. Okay, so now there is something called Canary Deployment, right? Where you have a pod, and then you have another pod. This one is G1GC. The first one before was Parallel GC. This one is G1GC. And then you have the service, the load balancer for those replicas. So here the load balancer is on port 80, attaching to port 8080. And then you have the other load balancer for the G1GC pods. And then we want the Canary deployment. So we're gonna do an ingress for Parallel GC, and we're gonna do 50%, here's 50, to G1GC. And we're gonna deploy all of that. So let's go into Canary, kubectl apply -f app deployment. And for this configuration, I did 3 replicas for each. So the Parallel GC here is configured with 2,000 millicore and 1 gigabyte of RAM with Parallel GC and 75% RAM. And the G1GC has the same limits and requests. kubectl get pods. We have G1GC, kubectl logs, up and running. Let's get the Parallel GC up and running. Now we're gonna deploy the ingress, kubectl apply -f ingress. Let's do a replace. I don't like this thing. Okay. So now we're gonna go into here. Let's go back into the kubectl get pods. No, I'm gonna go into the load test pod. kubectl get pods. Okay, kubectl get services. and kubectl get ingress. So if I hit the parallel GC, the other one should still get 50%. So I actually don't care about the ingress. I care about this IP address here. So we're gonna do work, 8 threads, 10 concurrent connections, 1 minute. I'm gonna put 2 minutes. And the IP address is the same. And I'm gonna do the inspect exercise. And what we want to see is half those requests going to the parallel GC pods and the other half to the G1 GC pods. And we should be able to see that here on the live metrics. There you go. So the G1 GC pods are here, and the parallel GC are here at the bottom.
I think you used the wrong IP address.
And am I using the wrong IP address again?
Using it of that service, so it's overall that service
Yeah.
ingress IP.
kubectl get ingress. Yeah, maybe I have to go here. I think it doesn't matter. Because both ingress have the same address. Yep, there you go. It's working. So what we see here is a bunch of requests going half and half to G1 GC, 3 replicas, and parallel GC, 3 replicas. The interesting thing about, I'm using Azure Application Insights, which is the Azure Apm. And one thing that I did was I put in the deployment, I put a role so I can separate parallel GC telemetry data versus G1 GC telemetry data. So I can actually come here and say role G1 GC. And I can see G1 GC data versus parallel GC data. And of course, this is during the live telemetry, but then I can also go into the reports and see and compare them hand in hand. So with this, I'm able to understand better the performance of both configurations in production at the same time. I can see that if I'm using this heap, my application performs this way. If I use that heap, the application performs that way. I'm using a load balancer to split. The application is still responsive, still works, but I'm able to see that in production with actual production data. That is one of the challenges with benchmarking in general, like this kind of web systems. How do you replicate, emulate production data? And usually it's better when you do benchmarking, looking at your performance in production, your data in production. So one thing that I would like to try to do, I have 10 minutes left. I just want to try to show you the difference between 6 replicas versus 2 replicas when you give more CPU and memory to the JVM. So let's try that. And again, like here, I'm not going to go into the details of the performance comparing G1 GC and parallel GC, but the intent here is to show you with Kubernetes and some ingress magic, you can do that comparison by yourself with your system and see which one performs better. All right, so let's go into redistribution. So we have 6 replicas, sample app, internal, and here's the service, internal sample app. So this one here I won't need the ingress, I just need the service. So let's clean it up, kubectl, get pods, actually get deployments, kubectl delete deployment Jvm GC, parallel GC, kubectl get services, kubectl delete service blah, kubectl delete service blah. This one here completed, kubectl get ingress, kubectl delete ingress, this one, parallel GC. Okay, so we cleaned up. Now let's do 6 replicas of this application. So we go into cubes, cd deployments, redistribution. kubectl apply -f 6 replicas. kubectl get pods. kubectl logs this one. Okay, up and running, kubectl get services. Okay, so we're gonna SSH into a pod to run the test from there. Load test. No, less clear. kubectl get services. We have the internal sample app. This is the IP address. (224.0.10) inspect. Okay, so now we have 6 replicas running with very little, not little, but small CPU and memory, and only on default heap size. And 1000 millicore with 500 megabytes. So let's see how this goes. So the pods are up and running. So we got about 4,000 requests per second with some variation. Peak to almost 6,000 and gets down again. (10,000 requests per second). I think I put 2 minutes to this. And then we're going to change this thing to the other one. So let me take a screenshot of this.
Inspect.
This was inspect, yes, not prime factor. The thing with the inspect, though, it does consume something because Spring Boot does his thing, right, behind the scenes. Okay. So the total requests per second, it kind of varies, right? And CPU usage also not stable. Now what we want to do is get this system a little bit more stable. So I have these 2 replicas, but cheaper. And by cheaper, I mean I'm going to do 2 replicas instead of 6, and 2000 millicore with 1500 megabytes. And I'm going to use parallel GC with a bigger heap. Okay, so this is the result that we got. I'm going to take this one. 8,000 requests per second. Benchmark. First run, 6 replicas. Now let's go into here, and we do kubectl apply -f, app deployment. Oh, I came in Canary folder. Kubectl apply -f, app deployment, 2 replicas, but cheaper. All right. Come on. Finish working. Okay, cool. So now instead of 6 replicas, I only have 2, but bigger. Okay, up and running. Let's run this again. Let me get the P99. Okay, there you go. Let's see how this one goes. Okay, so committed memory is higher compared to before. Before it was 200 only, now it's 400. CPU usage increased near 100%. The other thing interesting about CPU is you don't want 100%, but you also don't want 50% when you need throughput. You want to take advantage of the CPU as much as possible. All right, so the first data is usually like warm up, and you kind of ignore that a little bit. But in general, it does look like it's going better than before. And because I'm not looking into latency because unless it's CPU throttling, but because this REST endpoint is very fast, so there's not much point in looking into that. Even if I get a performance that is the same as before, this is better because I'm consuming less resources. Okay, now it's completed. So let's compare from visual here. So the first test ran with 7,000 requests per second. This one was 7.8 thousand requests per second. So more than 10% more requests per second than the previous one, even though it has less CPU and memory total. So I decreased CPU and memory total consumption, and I still got 10% bump in requests per second. If I look at the latency, my P50 got faster, P75 got faster, my P99 got faster. All of them got faster. And that's because the JVM has more CPU and memory to handle the things that it needs to handle. So with this, by just rearranging the resources, and I could show you 2 replicas, 3 replicas, but the intent is really to get down to the point where you reduce the total amount of resources under use, being used by your application on Kubernetes, to the point where you save money, and even better if the performance goes higher. If it stays the same, still okay. You keep resiliency, 2 replicas. You keep the system running at the same speed, but consuming less. But if you can get even better performance, that's a win. So we went from 6 replicas with 1,000 millicore, 500 megabytes using D4 Ergonomics to 2 replicas with parallel GC, 70% heap size, 2,000 millicore with 1,500 megabytes total memory. And you could still play around and you still find even better performance tuning if you go deep and look into the application, JFR data, garbage collection logs, and whatnot. So when it comes to looking into like, what can you do with your Kubernetes environment, Kubernetes cluster, so that you can reduce cost? By cost, I mean the cost of the running system, not total cost, because you provision, it's still a cost, but the cost of consumption of your system. And to do that, you have to understand your tech stack, and we learned this in the first part of this deep dive. You have to understand D4 ergonomics. Don't rely on them. Make sure that you set which garbage collector, you set the heap size, and understand the options of garbage collectors. Analyze and reorganize existing resources. Maybe you don't need to tune the application at all. Maybe all you need to do is just rearrange what your application is already consuming. So finally, understand the different workloads that you have, give more resources, have less replicas, not 1, still want some resiliency, but maybe reduce. If you have a microservice with 20 replicas and it's a microservice as like 500 millicore, 500 millicore, that's probably not the way to go. Maybe what you actually need to do is reduce the number of replicas, increase CPU and memory. So the bottom line is scale out and up as needed. So we always think about, I'm going to scale horizontally and I'm going to solve my performance problems. Most likely you will. Most likely, whatever you do with horizontal scaling, you will achieve your goals, but at a higher cost. And even so, perhaps you won't meet some performance targets that your system might have, like latency. So yeah, if you want to learn more about Microsoft and Java, go to that website, and you can follow me on Twitter. It's my name and my last name, Bruno Borges, on Twitter. And if you like this presentation and you have Twitter, please, I would appreciate some comments. My boss also appreciates that. And with that, thank you so much.